Welcome to Chapter 9, Part 2. In this section, we are going to talk about the first set of reactions for triple bonds. We are going to be looking at some addition reactions. So just like we added across a double bond, we're going to add across a triple bond. And so the first one we're going to look at, we saw how a double bond behaves with hydrogen and a metal catalyst like platinum, palladium, nickel, palladium on carbon. A triple bond is going to do exactly the same thing. You are going to add hydrogen, but you're going to add two equivalents, and you are going to go from an alkyne to an alkane. It works in the same way. You are taking that solid metal catalyst, right? It's just like a solid sheet of metal atoms. Little hydrogen atoms are going to absorb onto the surface. So little H2 molecules are going to break apart and the little hydrogen atoms are going to absorb. Your triple bond is going to come and interact, and it's going to pick up a hydrogen on both sides. And then the alkene that forms will react again. There's no way to stop it. So when you see this right here, yes, there will be an intermediate moment where you have a cis double bond, but you cannot stop it here. It is going to continue to react and react completely. Notice 100%. Reactions that give 100% yields are few and far between. This is one that is very effective, but it is not possible to stop at an alkene. Now, I'm an organic chemist, which means, as I've told you before, I'm a control freak. So what if I want to add to just one H2 molecule? What if I want to stop at an alkene? Well, I have good news for you. We have ways to do this. So this first one, we're going to call, it is not only catalytic hydrogenation, but this is a full reduction, a full hydrogenation. Now, I've mentioned this previously. Oxidation and reduction, I'm not redefining it from your Gen Chem classes, but we speak about it a little bit differently in organic, mostly because we're not as focused on the redox numbers. Oxidation is loss, reduction is gain. That is still true. If you went through and calculated oxidation numbers, you would find that oxidations, right, are going to lose electrons, so the charge is going to go up. Reductions, you gain electrons, the charge is going to go down. But since we're dealing with such a limited portion of the periodic table, we often talk about oxidation as increasing bonds to oxygen. Reduction is decreasing bonds to oxygen or increasing bonds to hydrogen. So this is a reduction. We are reducing these multiple bonds. So we can also do what we are going to refer to as a partial reduction. Partial reduction. Okay, my pen is gone haywire. Hold on a second. So look at the slide over here. We are doing a partial reduction. There we go. We have two options. We have an option that is going to take and I'll draw it linear, just so as not to confuse cis and trans. We have one reaction that will allow us to make a cis alkene. And we have another reaction that will allow us to make a trans alkene. Right? Neither one of these are both partial because we're adding one H2 molecule instead of two, which would be fully reducing it. And let's talk about the reagents. Now, to do a cis alkene, we need H2 and we still need a catalyst, but we're using something known as a poisoned catalyst. Specifically, the one I want y'all to memorize is Lindlar's. Lindlar's catalyst allows us to add hydrogen, but wind up with a cis double bond. Now, you don't need to know the mechanism, and you don't even need to memorize what Lindlar's catalyst is. Just know the name Lindlar's catalyst. It's quinoline with a palladium barium sulfate, and it is usually in methanol. Right? There are other examples of poison catalysts, like you see over here, this nickel complex. But again, they do the same thing, so I just want you to know one. I want you to know the most common one that we teach, an organic one, and that is Lindlar. Now, it is important that you still have H2. A catalyst isn't going to do anything by itself. So it's H2 and Lindlar's catalyst, no numbering. You want those both in there together. And so if you want to make a cis double bond, this is the guy you want to use. It behaves in a way that allows us to stop at the alkene. When we use H2 and a regular catalyst, right, it is going to bring down the activation energy of the steps so that we don't have this high barrier of activation. Well, H2 and platinum or palladium or nickel brings all of them down. But with the poison catalyst, it doesn't react with alkenes. And so the poison catalyst follows this energy diagram. So it brings down the activation energy of this first reduction. But then the activation energy for the H2 to react with the alkene is high enough that we can actually stop this reaction and collect the double bond at this point. We also, if we want a trans double bond, we are going to use something called a dissolving metal reduction. This is one that we are going to look at the mechanism. You are going to be responsible for knowing this mechanism. It's sodium and ammonia. It's very important that you recognize there is a difference between sodium and ammonia. Right, so Na, NH3 versus NaNH2. These are both reagents that you have to use in this chapter. They are different. They do different things. NaNH2 is a sodium ion and an amide ion. It's a strong base. Sodium metal is a neutral sodium atom and ammonia as a solvent, but also as a proton source. They do not behave the same way. If you do not write these down correctly, you do lose points. And that would include, don't write this down, just listen to what I'm saying here. If you write NaNH3 with no comma, I'm going to assume that, one, you either don't know exactly what reagents you're using, or two, you're trying to trick me, and I am not tricked. NaNH2 is one chemical formula. NaNH3 is another reagent. This is nothing, right? So that will get you no points. It is important that you recognize the difference. So let's look at our dissolving metal reduction. It's a really interesting mechanism. And of course, it's on this slide, but I like to draw while I talk. So we're going to talk through it. This is a very cool mechanism here. So let's start with 2-butyne and Na with NH3 to give us a trans 2-butene. The first step of this mechanism is actually a radical step. And we're going to talk all about radical reactions in chapter 10. But this is the first time we're going to use a single barbed arrow. So what happens is that sodium, we know that sodium is a group 1 metal, and it happily gives up its valence electron to be Na+, because it gives it that core noble gas electron configuration. And so what we wind up doing is we wind up donating that electron to one of the carbons in the triple bond, and then we get a homolytic cleavage instead of heterolytic. Notice I am using single barbed arrows. We're indicating the transfer or the movement of a single electron. So now the carbon on the left is a radical. It got one electron from the pi bond. The carbon on the right got the other electron plus the one from the Na. And, oh, there's just a carbon over there. So what we have is called a radical anion. Now, the way I should have drawn it, if I want to think about the actual geometry, is the radical and the anion adopt this sort of trans configuration, kind of spreads out the pain a little bit. The negative charge of the radical and the negative charge of the lone pair want to get as far apart as possible. And so to maintain the other pi bond that's still there for the double bond, they adopt this sort of trans arrangement. Then because we have NH3 around, now ammonia is not considered an acid, but a carbon with a negative charge, especially one in a double bond, is really uncomfortable. So this is actually a really strong base, and it will steal a proton from your ammonia. So the first step gives us a radical anion. The second step leaves us with, a radical. The third step uses another sodium ion. So we are going to use a single barbed arrow. It donates that radical to, it donates that electron to the radical. Radicals are relatively unstable, and electrons would rather be paired in this instance. And so we wind up making an anion intermediate. All right, so we go radical, anion, to radical, to anion, right? So there's 3 types of intermediates in this mechanism. It's a pretty cool mechanism, right? And so this doesn't match all the patterns you learned in chapter 6, although you do have a proton transfer there in the middle. Radical reactions are a little bit different. The last step is that anion, again, very unstable, wants to react. It's a very strong acid. It wants to pick up that proton from our base. I shouldn't say from our base. Wants to accept our proton from our acid. In this case, ammonia, of course, is acting as our acid. And this will give us our trans alkene product. So I do expect you to know this mechanism, right? I can't ask you to draw it on an exam, but I will ask you about the intermediates. You will have to work on the arrows in your homework. And this dissolving metal reduction is a really cool new mechanism. The slides go through each step just as we did throughout this video. So you can walk through those and read them as well. So when we talk about reduction of alkynes, here is a summary. You can take a alkyne to an alkene, a cisalkene, a transalkene, or all the way down to an alkane. And everything can be taken to an alkane with H2 and platinum, or palladium or nickel. The next set of reactions are hydrohalogenation. So this is very similar to an alkene addition that we saw. We know that if we add HX across a double bond, we get a Markovnikov addition. So hydrohalogenation is going to work very similarly for alkynes as it did for alkenes. It is going to be a Markov-Nikov reaction, meaning the X goes to the more substituted side. Now, in this case, it matters how much reagent you use. If you have a triple bond and you use one equivalent of HX, usually HBr or HCl, you will make a halogenated alkene. You'll add H to the less substituted side and the halogen to the more substituted side. If you use any more than one equivalent, so you could either see two equivalents or you might see excess, just for you have more than you need, excess HX, it's going to add twice. And both times the X is going to go to the more substituted side. So this is a way to make a geminal dihalide. I am not concerned with you thinking about the mechanism. It would seem that it should be the same as the mechanism for adding one HX to an alkene, but this thing right here in the middle that you'd see in the middle, vinyl carbocations, are so unstable that this isn't likely. So when looking at kinetic data, when looking at thermodynamic data of intermediates, that mechanism doesn't seem to make sense. So I'm not going to teach you something that isn't likely. We're not sure exactly what the mechanism looks like, although it probably has some cool transition state like this in the middle. This will not be a mechanism that you are asked to know. So that last one, right, dissolving metal reduction, that's a mechanism I want you to know. This one, I don't. I just want you to be able to predict the products. Now, if we want to add Antimarkov, we can. And we can do that in the same way, right? So anti-mark, hydrohalogenation. We're still going to use HX and ROR, right? Not two separate steps. They go together. We would need our peroxides. We're not going to worry about the E and Z isomers. You get a mixture of both. If you only use one equivalent of HX, you will only add one alkyne. I'm sorry, not alkyne. You'll only add one halogen to the alkyne. So if we start off again with our alkyne, and it will either be bromine or chlorine. Iodine doesn't work well here. It will only be bromine. So let's not even put in X. Let's just put in HBr. Iodine doesn't work as well in a lot of reactions. In this case, chlorine doesn't either. We're going to see that again in chapter 10. You will notice I use bromine a lot more than the other halogens. It just tends to work better than some of our other halogens, either for kinetic reasons, like with chlorine and iodine maybe just going slower, or it might be selectivity reasons, or it's compared to fluorine. Fluorine does a whole bunch of other stuff, so we just stay away from fluorine for now. And this will, if we put one equivalent of HBr and ROR, we will add one halogen to the less substituted side. Oh, okay. So something to note here is dihalides. Well, why would we stop there? You could do excess. It's not as reliable, but it can work. But it will add both to your anti-mark side. Now, we know how to make geminal dihalides either with HX or with HX and ROR. We also know that dihalides, whether they are on the more substituted side or the less substituted side, we learned earlier if we treat them with NaNH2 in an excess amount, and then work them up with water. That's a way we can make triple bonds, right? So we can make gem dihalides and we can make alkynes. So it just depends on what conditions we want to use. That's going to be really helpful for synthetic purposes. In the next video, we'll talk about hydration of triple bonds.